All right, let's move into something we call the law of conservation of energy. You may not know it, but you've actually heard this before, probably. And it's going to be a really similar topic, a really similar thing to what we talked about when we did the work energy theorem. Law of conservation of energy, I put the letter COE there because you'll sometimes see COE, and we use that to abbreviate conservation of energy. So let's go ahead and get started. So the law of conservation of energy actually says this. It says in a closed system, the total amount of energy in that system remains constant or stays the same. And another way to say that is that energy is conserved. That word conserved, sometimes I tell my students, if you think about what it means to be a conservative person, it could mean a lot of things to a lot of people, but the definition of a conservative is someone who wants things to stay the same. And so when we talk about things in physics being conserved, or in biology, right? We want species to be this conserved. That means we want things to stay the same. We don't want things to go away. We don't want things to change. So the law of conservation of energy says that energy stays the same in a closed system. And there's an asterisk there because I'll talk about what a closed system means in just a minute. But energy is conserved in a closed system. Energy can change forms. We've already talked about two forms of energy, kinetic and potential. We'll continue talking about those today. It can change forms from one to another, but the total amount still remains the same. This is really similar to a bank account. If you have a checking account and a savings account, usually if you have a job, you get paid and that money gets deposited into your checking account. Say you get paid $200. Well, if I transfer $200 from my checking account to my savings account, the relative amounts of those accounts have changed. My checking account went down $200, but the savings account went up $200. Those amounts changed, but the total amount of money that I have didn't change at all, because that can sort of be considered a closed system. No money came in, no money came out. This is also known as, you've heard it this way before, that's what I was referring to earlier, energy cannot be created or destroyed. We know energy can't be created, it can't be destroyed. That means it doesn't just pop up, doesn't just show up out of nowhere, and it doesn't just disappear. Now let's talk about what this closed system thing means. So in a closed system, we said the total amount of energy remains constant. Closed system simply means, gotta find somewhere to put this, closed system simply means that it's a group of objects that gains or loses no energy. No energy comes in and no energy goes out, right? So, and this is very hypothetical. It's kind of difficult to come up with a really good example of what this would be. But we're going to use this as a guide for thinking about what conservation of energy means, right? So closed system means no energy is going to come in, no energy is going to go out, kind of like my checking and savings account, as long as I'm not spending anything. Really important that we understand that means there's going to be no friction in any of these problems. If there is friction, remember, friction converts kinetic energy to heat. So that means in our closed system, friction acts kind of like a leak. Some of that kinetic energy, friction causes some of that kinetic energy to go away. It turns into heat energy, and the heat just dissipates to the environment, and we can't reuse it anymore. If there is friction in a system, that means it's not a closed system. And you might have guessed that, yes, there are almost no truly honestly closed systems in the universe. But it helps to sort of imagine a closed system in our minds so that we can begin to talk about concepts like the conservation of energy. Now, when we get to conservation of energy, we need to understand that really all forms of energy are conserved. All of them. All the forms of energy, all the ones that we're going to be talking about later on, energy is conserved all the way across the board, right? It doesn't matter what kind of energy you think about. But today, just for our purposes, to keep it simple, we're still just going to stick with mechanical energy for now. We're just going to deal with potential and kinetic energy. So that means at any one time, doesn't matter what's going on, whether we got something sliding down a hill, something's falling, whatever's happening, at any time during that scenario, we can calculate the total amount of energy by calculating that object's potential energy, calculating the object's kinetic energy, and then adding the two of them together. Those two individual amounts can change, but the total amount has to stay the same. Again, kind of like your bank account. The total amount of money that you have is going to stay the same. Your checking account might change, your savings account might change, but at any time you can calculate your total amount of money by adding those two together. And for us, our total energy is going to stay the same because we're going to deal with closed systems. I want you to make sure you write this down. There are going to be three kinds of scenarios that we deal with conservation of energy. Three kinds of problems that I want you to look for. The first one is a roller coaster, right? Any kind of problem that has a roller coaster in it, guarantee you that's a problem where you're going to be using the law of conservation of energy to solve it. Second kind of problem is a pendulum. Anything swinging back and forth, and there are lots of different examples of pendulums. For instance, a child swinging on a swing. That's an example of a pendulum. And the third type of conservation of energy problem is a free fall. And remember, free falls are objects that are being thrown up in the air. That object is falling as well. It's just falling up because gravity is still pulling down on it, causing it to slow down. Free falls also could be objects that are moving downwards. So thrown up in the air, falling down, both of those are free falls. Both of those are going to be examples of what we use for conservation of energy problems. Again, all of these have no friction. If there was friction, it would be a little bit more difficult to solve the problem. Not impossible, but just a little bit more difficult. So for our purposes, we're not going to use any friction in these problems. So let's look at some of the problems for conservation of energy.